are going to learn about multiple random variables from chapter 5. The content of this chapter are joint CDF, PDF, PMF, conditional distribution, mean and variance, and finally covariance and correlation coefficient. Let's recall some basics. We have already covered some of the properties of CDF. So we have seen this. If we want to find the probability within a range for each of x and y, two random variables, so we can use this formula. At first we can see we are considering only variable x for the range, and we can see that here in fxy we are putting the range x2 and x1 while y is fixed. Similarly, we can do it in otherwise for the considering variable y. Again, if you want to consider the range of both x and y, we can use this formula. We have discussed this formula in our earlier class, and we also discussed about joint PMF properties, and it is similar to that we have learned in chapter 2. The total probability should be 1. It is for discrete. You can see the PMF, and we also have learned how to find the marginal PMF from joint PMF. When we are finding the Px, we have to consider all the possible values for y, and similarly when we are finding Py, we have to consider all the possible values of x. And we also discussed about independence, condition for independence. If x and y need to be independent, then pxy should be equal to px into py. Similarly, for continuous random variable, now we will talk about the conditional distribution. We have seen this in our last class. We have two conditional PMF. One is Py of the x, that means the probability of x equal to x is given. This is given. So we now have to find the probability of y. So we are going to divide the joint PMF Pxy with Px. Simple as that. Similarly, when we are going to find the probability of x, given that y equal to y, the probability can be calculated using this formula, joint PMF divided by Py. Let's see an example, 5.8. We have seen this already. Pxy is given, the joint PMF. Here we can see only 2 values of x and 3 values of y. So at first we will find the marginal PMF Px and Py, and only then we can find Pyx and Pxy. So let's find out the marginal PMF. We know when we are calculating Px, we will consider all the possible values of y, that is from 1 to 3. So we are using 3 values of y in this formula to get the Px, and which is 1/5 into x plus 1. And similarly, we can find Py. And finally, using the above formula, we can find the conditional probability Pxy or Pyx. So let's see another example on continuous random variable. So for continuous, we will follow the same formula, joint PDF divided by marginal PDF. And let's see an example, 5.9. So this is our joint PDF, and we are at first we are going to find the marginal PDF, fx and fy. Fx can be calculated when we are going to integrate the joint PDF with respect to variable y. Similarly, fy can be calculated when we are integrating the joint PDF with respect to dx. Don't forget the limit is from 0 to infinite, because that is the valid range for x and y. So here while calculating fy, we have to use the uv formula. We can let u equal to x and t is equal to e to the power minus x into y plus 1, and following that, if you follow the uv formula, you will finally get 1 over y plus 1 whole square. So once we find the fx and fy, we can now directly use the above formula, these two formula, to calculate fx oblique y or fy oblique x. So this is the answer. Now I think this topic is the new topic, so let's focus. Today we are going to learn conditional means and variance. For discrete random variable, conditional means mu y oblique x. It means that we are going to find out the expected value of y, but there is a given value of x equal to small x. So this is the same basic formula from chapter 3, except that instead of using probability PDF Py, we are going to use Py oblique x. That means conditional probability. So there is nothing new here. Only we are changing the Py with Py oblique x. So that is, this part is change. So it was previously just Py, now it is Py oblique x. That's it. Similarly, when we are finding the variance, we have to consider the same old formula from chapter 3, except that here we are using the conditional mean instead of simple mean mu y. We are considering mu y oblique x. So this is the new, and also the probability px is being changed with, I think this is py oblique x. This is a typing mistake, so just consider that. So this will be py oblique x, not x oblique y. Anyway, so now finally we are getting something similar to m2 minus m1 square. You know, you can recall from chapter 3, the variance can be calculated from the expected value of y square minus expected value of y whole square, which is m2 minus m1 square. So what is the difference here? The difference is that we are calculating the expected value of y square with a given condition x equal to x, and similarly expected value of y with a condition x equal to small x. Now, for continuous random variable, the formula is same, except that we are using PTF instead of PMF. So this is the same old formula from chapter 3, y into probability of y with a given condition of x, and same is for variance. Let's do the example 5.10. So here we can see the probability fxy is given for a range, particular range. Now we are going to find the mean and variance. For the mean fy, for the mean of, to find the mean, we have to find at first the marginal PDF, because without marginal PDF we cannot find the conditional PDF, which we are going to use to find the conditional mean. So we are going to find the marginal PDF, which is fy is equal to something like e to the power minus y, and then we can find fx oblique y by dividing the joint PDF with fy. So this is it, and then we can find the conditional mean of x for a given y like this. So here you can see x into probability of x, which is with a given value of y. So we are using this x and the new value of x oblique y here to find out our final answer, and you have to use the UV formula here to solve the integration, and finally we will get the value is y. I think all of you should practice at least one example for conditional mean and variance. These examples are, some of the problems are given at the end of this chapter. So next, what we are going to focus is covariance and correlation coefficient. For covariance, covariance is defined like this. which is expected value of x minus mu x into y minus mu y. So if we want to derive this, we can rewrite the expression like this. For example, here we have two terms. We can simplify. We can write them in this format, and we can distribute this expectation operator on each of these four terms. When we are distributing, we can see that this expectation operator will only be active on the random variable x, y, but it will not be active on a constant like mu y. Here we can see that x is a random variable, but mu y is not a random variable, it is a constant. So the mu y will be out of the expectation operator. So expectation operator will only operate on x. Anyway, we can rewrite this expression in this way, and we can finally see that there will be cancelling out, two terms will be cancelled out, and finally we will get the answer expected value of xy minus mu x minus into mu y. So that is the covariance. So what does covariance mean? Covariance means if there is a kind of correlation between the two random variables x and y. Usually the value of covariance is higher when the correlation between x and y is high. There is some kind of relation, and the covariance value will be higher. Similar to covariance, we will define another thing which is called correlation coefficient. So we will get it by dividing covariance with sigma x and sigma y, which is a square root of variance of x and variance of y. So by dividing covariance with these two terms, what will happen is this, that the value of correlation coefficient will remain in between this range, that is -1 to +1. Here so you can see that. So now you can guess the difference between covariance and correlation coefficient. Correlation coefficient will be limited within this range, but covariance will not be limited within some particular range. It will depend on the random variable itself. So anyway, if the absolute value of correlation coefficient is very close to 1, that means the value is close to -1 or close to 1, it indicates a high degree of linearity between x and y. It means that there is a strong relation between x and y. When that means it will follow some kind of straight line relation. And when the correlation coefficient is 0, it means there is no linear correlation between x and y. Let's see an example. I think all of you should follow one principle. When you are going to next slide or next topic, better to say next topic, you should practice at least one example from the book that you just understand, so that there is no confusion about the topic. And then after practicing one example, you should move to the next topic. Anyway, let's see another example of covariance. So we are given with a joint PDF. Now we are going to find, at first we are going to find the marginal PDF fx and fy. You can find just like before, and we can see that this random variable x is following a uniform distribution. We have talked about this in chapter 2 and chapter 4. Uniform distribution is that within for a particular range the probability is constant, and for this kind of uniform distribution we can use the formula available from chapter 4 directly, and using this formula we can find expected value of x is equal to, as you recall, it was like b plus a divided by 2, something like that. So the expected value can be directly calculated using that formula, which is here 0.1. Similarly, we can see that y is following exponential distribution. We know that for exponential distribution the expected value is 1 over lambda. Here lambda is equal to 5, so the expected value is 0.2. So now to find the covariance we also need expected value of xy. This is something new, we did not practice it before. So to find the expected value of xy we have to integrate it twice, one for x and another for y. So we have to use the limit individually for x and y here, and using, at first we can do it for y and then we can do it for x, and if you do it properly you can see that when we are dealing with we are integrating with respect to y, there is a 2 term y and e to the power something y, so you have to use the UV formula again to find out that the value of this is just 1, and then we can integrate with respect to x, and finally you will come up with the value 0.02. So it's important that you practice this kind of integration so that you don't make mistake in the exam. And finally we will get the correlation covariance, which is expected value of xy minus mu x into vy, and we can find that the covariance is 0. So what does it mean? Covariance is 0 means correlation coefficient is also equal to 0. It means that the x and y are uncorrelated. However, it is interesting that we can come to this conclusion that x and y are uncorrelated, or the covariance will be 0. We can actually directly come to this conclusion from another way, which is we can show that fxy is equal to fx into fy. When we already found the marginal PDF fx and fy, you can see that if we multiply this with this, we are getting the joint PDF. So when we can show that this equation is satisfied, we can directly say that x and y are independent. If they are independent, the covariance should be equal to 0, and x and y are uncorrelated. We can come to this conclusion directly. And I hope you if you have not practiced an example based on our previous topic, you should practice that again, practice that first and then come to the next topic. Our next topic is many random variables. We will see one particular distribution, multinomial distribution. So far we are only talking about 2 random variables, x and y. Here we will talk about more than 2 random variables, and we will consider a variation of binomial distribution, which is called multinomial distribution. So multinomial distribution is an extension of binomial, and we will follow this formula for multinomial distribution. So what is the difference between binomial and multinomial? In binomial distribution, you can remember that we only consider Bernoulli trial where there is only two events, either success or failure. But in this case, we have more than two outcomes. For example, here m number of outcomes. So what are these k1, k2 and km? So k1 is the number of outcome for event 1, k2 is the number of outcome for event 2, etc. And this is the formula, and in this formula we can see p1, p2, etc. So p1, what is p1? P1 is the probability that event 1 will take place, and p2 is the probability that event 2 will take place, etc. Let's see an example. 5.15. So in this example, a fair die is rolled 7 times. Find the probability that number 1 appear twice and the number 2 appear once. So how many outcomes are here? At first we have to decide it. Try to focus and try to understand how many outcomes are here. We are talking about a fair die which has how many outcomes? 6 outcomes. But in this problem, how the questions are written, let's focus. The number 1 appeared twice. That means number 1 is an outcome. So it will appear. That means k1 is equal to 2. Number 2 is another outcome, and k2 equal to 1. Okay. So how many outcomes are here? Is it 2 or is it 6? Actually, because the question is only talking about number 1 and number 2, and so we have to consider these two events. And in addition, the question is also saying that the die is rolled for 7 times. So if number 1 appear twice and number 2 appear only once, that means 3 times, right? So what are the other 4 times? The other 4 times include the outcome from number 3 to number 6. So all of those outcomes, number 3 to number 6, that means 3, 4, 5, 6, these 4 outcomes will be grouped together as a single outcome. It's like failure. You remember the binomial, right? The success is defined as one outcome. The other than success, which is failure, is defined as another outcome. So it's like we can interpret it like this one. Number 1 is success number 1, number 2 is the success number 2, and all of them, that is 3, 4, 5, 6, all of them can be considered as failure or outcome number 3, or even 3. So let's see the solution. So instead of normal 6 events, we have here 3 events. The first event is when we will get number 1, the second event is when we are getting number 2, and the third event is when we are getting from number 3, 4, 5 or 6. So we will apply our formula here. We can see that for even number 1, the k1 is equal to 2. For even number 2, k2 is equal to 1, and the rest of the 4, where we are getting this 4? So this 4 is coming from 7 minus 2 minus 1, that is equal to 4. So this is it. So this is the formula. So using this formula, we will get the probability. And don't forget to write down the probability of each outcome. Here it is noticeable that 1 by 6 is straightforward. You understand how the 1 by 6 we get the 1 by 6 for each of the fair die. Each of the outcome from the fair die is 1 by 6, but as we are considering 4 outcomes together as our event number 3, so the probability is 4 by 6. So don't make mistake here. So that's